So in this video, we're going to take a look at just an incredibly important, this may be one of the most important things we're going to talk about when we talk about charges, and that is the idea of polarization. Polarization explains so much of what happens with charged objects, and the problem is that it really requires a deep understanding of the nature of matter. And that is something that in middle school, they're just not going to reveal to you. So in middle school, you might learn that like charges repel and that opposites attract, but that doesn't really explain why is it when you rub a balloon against a sweater, it'll stick to the wall, or you may even be able to get it to stick to the ceiling. What's going on there? The wall or the ceiling weren't charged. The wall or ceiling certainly didn't have the opposite charge of the balloon, so why does the balloon stick if the wall wasn't charged in the first place? And it really comes down to this idea of polarization. So polarization is the separation of charges. Normally, most objects are neutral, meaning that if you were to look at the object, I'm going to draw some positive and negative charges in here, just like we did in the last video. Okay, so I drew 6 positives and 6 negatives. This is a neutral object. The charges are, of course, going to be evenly distributed because the positives, they don't like to get near each other, and the negatives, they don't like to get near each other. So what they're going to do is to spread themselves out as much as they possibly can so that the negatives are as far apart as they can get from each other, and the positives are as far apart as they can get from each other. And ultimately, if you were to look at this object in any different direction, it basically looks the same because you see positive, negative, positive, negative, positive, negative. You see the charges essentially nice and evenly distributed. But when you bring a charged object nearby, depending on what kind of material this is, you're going to see that the charges are going to begin to move around. And so this idea of polarization is the idea that we're going to separate the charges from each other. It's still going to be neutral. Okay, this is not a video about charging objects. I'm not going to charge any of the objects in here. I might bring in a charged object, but I'm not showing you how to charge objects. I'm simply showing you what happens to neutral objects when you bring charged objects close by and they become polarized. Polarizing means kind of like having an orientation to something, that it matters how something is oriented. Now, right now, this atom doesn't have any orientation because it's a sphere. The charges are all evenly distributed. Whether I look at it this way or this way or this way, what I'm going to see is alternating charges, no matter how I do it. I don't see any place where positive or negatives are pulled together. It's very much like the way your hands are. Okay, your hands are identical in a sense, but they're identical in a mirror image kind of sense. So for example, my thumbs are pointing together in the same direction. My fingers are pointing in the same direction, but look at my palms. They're pointing in the opposite direction. Now I could turn my hand so that now my palms line up in the same direction. My fingers line up in the same direction, but look, my thumbs are now pointing in the opposite direction. There is no way, I will never be able to turn my two hands so that they look exactly the same with the same orientation. Just as though the positive and the negative are just like that. They're essentially the same thing. Positive and negative charges are the same things. They have the same kind of influence on the surrounding materials, but there is a difference between them. It's essentially in the same way that my hands are the same and yet opposite, that is what charges are. So in this particular instance, this thing has no particular orientation, and it's a neutral object. Now let's take a look at what happens to different types of objects. Let's take a look at what happens to conductors and what happens to insulators. Okay, so when a conductor becomes close to a charged object, the charges in it will begin to feel that charged object. So in this case, let's say I bring in a plastic rod and I rub that plastic rod against a piece of fur or like a piece of wool, something like that, and some negative charges have rubbed off on that object. Okay, now here is that same object. This is called a pith ball. It's a conducting material. What happens to the charges? So remember, here's what the original pith ball looked like. It was neutral. Everything is distributed nice and evenly all over the place. It doesn't have any orientation. It's not like more negative on one side or more negative on the other. But when I bring this guy down close by, the negatives do not like him. So all the negatives that I drew up here, I drew 6 negatives in this picture. All of the negatives are going to do something like this. They are going to move over away from this guy because they're repelled from him. On the other hand, the positives are attracted. So the positives are going to move this way. Now, did the positives really move this way? No, they didn't move that way. They were always there. There's always positives everywhere inside of all objects. What happened was that some of their negatives their free electrons moved away from them, and that left this side more positive than negative. That's why this appears to be so positive. If I brought you in and made you a tiny little person and you stood next to this object, you'd say, oh, this is very, very positively charged. I can really feel the positive charge. And if I moved over to this side, you'd say, oh, this is very negatively charged. I feel all this negative charge. It's really close to me. But if you step back away, you would see that, no, it's actually not charged at all. It's still a neutral object. 6 positives and 6 negatives. This object is still neutral. But this little separation, that little separation of charge, that is what is referred to as polarized. So this object has been polarized. It has orientation now. There is a positive side. There is a negative side to this thing that there wasn't there before. So it has an orientation now. There's kind of an orientation to it. It matters which side that you look at because you're going to experience something very different. Now, really important, again, to recognize that only the free electrons moved. Only the free electrons moved. Okay, that's something that conductors have. That's what allows them to have such significant polarization, because those free electrons can go wherever they want. So they can collect over here along this side. It's no problem whatsoever. Now, on the other hand, insulators behave similarly, but with a slight difference. And so let me show you insulators. So let's take a look at what happens there. Remember that in an insulator, there are no free electrons. So nobody is free to just move around wherever they want to go. So if you remember in the previous picture of what it looked like when we had objects that were insulating material, we saw that back up here that these guys were bound together. That it wasn't just a bunch of positive negatives, kind of, no, they're not randomly distributed around. They're bound together. They cannot leave each other. So down here, you actually will still get some separation of charges, but it's going to look something like this. So within each atom, the positive side will shift slightly towards the negatively charged object, while within the same atom, the electrons will move away. So the electrons did not leave the atom, but they did move a little bit, so that you'll see that the atom itself becomes polarized with a slightly negative end, and then there's also a slightly positive end. And as a result of that, this object will become polarized. Now, every atom that is inside of this insulating material is going to do the same thing. So all of the positives are going to move over closer to the negatively charged rod, and all the negatives are going to kind of squish over, to the side within the atom so that they are farther away. And every atom is going to do that same thing. So let's draw all 6 of the atoms that I showed in this one. They're all going to have their positive side on the left and the negative side on the right, and these guys the same way. So that little tiny separation, that's the polarization. So this one is also polarized, but it will tend to be a little bit weaker. It won't be as strong a polarization as you would see in the conductors, but you will still get polarization. And this is really going to help explain, why did that balloon stick to the wall? Why does a balloon, when you rub it against something and you allow it to pick up a little bit of charge, why is it attracted to everything? What causes that attraction? And that attraction is caused by the polarization. And it doesn't matter whether you're a conductor or whether you're an insulator. If you come nearby a charged object, you will become polarized. Super important that you understand. I'm not saying they're charged. Neither of these objects is charged. It's just simply that they act a little bit like they're charged, in the sense that they have separated their charges from each other, so that the positive and negatives have kind of started to pool on one side or the other. This insulator is more negative on the right side and more positive on the left side. Not quite as dramatic as the conductor, but still, this guy did become polarized.